Welcome to our comprehensive exploration of electromagnetic waves. In this video, we'll examine how these waves propagate through space, the relationship between electric and magnetic fields, and the fundamental equations that govern their behavior. Let's begin by understanding what electromagnetic waves are. Electromagnetic waves are oscillations of electric and magnetic fields that propagate through space, carrying energy and momentum. These waves travel at the speed of light in vacuum, which is approximately 300 million meters per second. Unlike mechanical waves, electromagnetic waves don't require a medium to travel through, they can propagate through the vacuum of space. The behavior of electromagnetic waves is governed by Maxwell's equations. These four elegant equations completely describe how electric and magnetic fields are generated and how they interact. First, we have Gauss's law for electricity, which states that the divergence of the electric field equals zero in vacuum. Second, Gauss's law for magnetism tells us that the divergence of the magnetic field is always zero, meaning there are no magnetic monopoles. Third, Faraday's law of induction shows that a changing magnetic field creates an electric field. And fourth, Ampere's law with Maxwell's correction reveals that a changing electric field creates a magnetic field. Together, these four equations form a complete description of electromagnetism and predict the existence of electromagnetic waves. From Maxwell's equations, we can derive the electromagnetic wave equations. For the electric field, we get del squared E equals mu naught epsilon, naught times the second partial derivative of E with respect to time. Similarly, for the magnetic field, we get del squared B equals mu naught epsilon, naught times the second partial derivative of B with respect to time. Both of these equations take the form of the general wave equation, confirming that electric and magnetic fields can propagate as waves through space. Now, let's visualize an electromagnetic wave propagating in 3 dimensions. We'll set up a 3-dimensional coordinate system where the wave will propagate along the positive z-axis. The electric field, shown in blue, oscillates along the x-axis, while the magnetic field, shown in red, oscillates along the y-axis. As the wave propagates through space along the z-axis, both fields oscillate in a sinusoidal pattern. Notice that the electric and magnetic fields are in phase with each other. When one reaches its maximum amplitude, so does the other. Let's now examine the mathematical representation of our electromagnetic wave. For a wave traveling in the positive z direction, we can express the electric and magnetic fields as follows. The electric field vector E equals E naught times sine of k z minus omega t times the unit vector in the x direction. The magnetic field vector B equals B naught times sine of k z minus omega t times the unit vector in the y direction. There's an important relationship between E naught and B naught. E naught equals c times B naught, where c is the speed of light. Both fields oscillate sinusoidally with the same frequency and are in phase with each other. The quantity k z minus omega t represents the phase of the wave, where k is the wave number and omega is the angular frequency. Now, let's look at a cross-sectional view to better understand the phase relationship between the electric and magnetic fields. Here, we're looking at the wave from the side, perpendicular to the direction of propagation. As time progresses, both the electric field, in blue, and the magnetic field, in red, oscillate in perfect sync. They're exactly in phase. When the electric field reaches its maximum, so does the magnetic field. When the electric field passes through zero, the magnetic field does too. Note that the fields are always perpendicular to each other and to the direction of propagation, forming what we call a transverse wave. Electromagnetic waves transport energy through space. The energy density of an electromagnetic wave includes contributions from both the electric and magnetic fields, and is given by U equals 1/2 epsilon naught E squared plus 1/2 over mu naught B squared. The direction and rate of energy flow is described by the Poynting vector, which is the cross product of E and B fields divided by mu naught, S equals E cross B over mu naught. For our wave, the Poynting vector points along the direction of propagation, the z-axis. This tells us that energy flows in the same direction that the wave travels. Electromagnetic waves cover a wide range of frequencies and wavelengths, forming what we call the electromagnetic spectrum. From low frequency to high frequency, the spectrum includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Visible light is just a tiny slice of this spectrum, corresponding to wavelengths between approximately 380 and 750 nanometers. Despite the vast range of frequencies, all electromagnetic waves share the same fundamental properties we've discussed and follow the same Maxwell's equations.